Hello, we are back at the FinetLink channel, and uh, as you know, we are at the module of switching, routing, and wireless essentials. And today we will be learning the switching concepts. As you know, for the moment, you can connect and configure switches, and that's great. But even a network with the newest technology develops its own problems eventually. So if you need to troubleshoot your network, you need to know how the switches work. And here we will give some fundamentals of switches and switch operation. And the objective of this material is to explain how layer 2 switches forward data. So we will explain how frames are forwarded in a switch network, and we will compare a collision domain to a broadcast domain. The concept of switching and forwarding frames is universal in networking and telecommunication. Various types of switches are used in LANs, WANs, and in the public switched telephone network. The decision on how a switch forward traffic is made based on the flow of the traffic. There are two terms associated with the frames entering and leaving an interface. We have ingress. This is used to describe the port where a frame enters a device, and the egress. This is used to describe the port that frames will use when leaving the device. A LAN switch maintains a table that is referred when forwarding traffic through the switch. The only intelligence of LAN switch is the ability to use its table to forward traffic. A LAN switch forwards traffic based on the ingress port and the destination MAC address of an Ethernet frame. With a LAN switch, there is only one master switching table that describes a strict association between MAC addresses and ports. Therefore, an Ethernet frame with a given destination address always exits the same egress port, regardless of the ingress port it enters. There is an animation here that shows the switching process. And as you can see, when the port enters, it checks for the destination address and follows the MAC address table and find which port is associated with that MAC address. If it will come at the port 3, check the destination is AB, and AB is referred to the port number 6, so the port number 6 will be the egress port. A switch is made up of integrated circuits and accompanying software that controls the data path through the switch. Switches use destination MAC addresses to direct network communication through the switch out of the appropriate port toward the destination. For a switch to know which port to use to transmit a frame, it must first learn which device exits on each port. As the switch learns the relationship of ports to devices, it builds a table called a MAC address table. This table is stored in contact address memory, which is called CAM, and which is a special type of memory used in high-speed searching application. And for this reason, the MAC address table is sometimes called even a CAM table. LAN switches determine how to handle incoming data frames by maintaining the MAC address table. A switch populates its MAC address table by recording the source MAC address of each device connected to each of its ports. The switch refines the information in MAC address table to send frames destined for a specific device out of the port which has been assigned to that device. And there are two-step processes that are performed on every Ethernet frame that enters a switch. We have the first step, which is the learning, examining the source MAC address. Every frame that enters a switch is checked for new information to learn. It does this by examining the source MAC address of the frame and port number where the frame entered the switch. If the source MAC address does not exist in the MAC address table, the MAC address and incoming port number are added to the table. And if the source MAC address does exist, the switch updates the refresh timer for that entry. And by default, most Ethernet switches keep an entry in table for 5 minutes. If the source MAC address does exist in the table but on a different port, the switch treats this as a new entry. The new entry is replaced when the same MAC address but with the more current port number. And the step 2 is the step of forwarding, where the switch needs to examine the destination MAC address. And if the destination MAC address is a unicast address, the switch will look for a match between the destination MAC address of the frame and an entry in its MAC address table. If the destination MAC address is in the table, it will forward the frame out of the specified port. But if the destination MAC address is not on the table, the switch will forward the frame out of all ports except the incoming port. This is called an unknown unicast. If the destination MAC address is a broadcast or multicast, the frame is also floated out all ports except the incoming port. And switches make layer 2 forwarding decision very quickly. This is because of the software on application-specific integrated circuits, which reduce the frame handling time within the device and allow the device to manage an increased number of frames without degrading the performance on the network. Layer 2 switches use one of two methods to switch frame. We have the store and forward switching, and this method makes a forwarding decision on a frame after it has received the entire frame and checked the frame for error using a mathematical error checking mechanism known as a cycle redundancy check. Store and forward switching is a Cisco primary LAN switching method. The store and forward switching has the following two primary characteristics. It has an error checking because after receiving the entire frame on the ingress port, the switch compares the frame check sequence value in the last field of the datagram against its own frame check sequence calculation. The frame check sequence is an error checking process that helps to ensure that the frame is free of physical and data link errors. If the frame is error-free, the switch forwards the frame, otherwise the frame will be dropped. And it has even an automatic buffering, because the ingress port buffering process is used by store and forward switches by providing the flexibility to support any mix of Ethernet speeds. For example, if you need to handle an incoming frame traveling into 100 megabit per second Ethernet port that must be sent out of 1 gigabit per second interface would require using the store and forward method. With any mismatch in speed between the ingress and egress port, the switch stores the entire frame in a buffer, computes the frame's check sequence check, and forward it to the egress port buffer and then send it. And here there is an illustration how to the store and forward make a decision based on the Ethernet frame. We have even the second method of switch for forwarding the frame, which is cut-through switching. This method begins the forwarding process after the destination MAC address of an incoming frame and the egress port have been determined. The store and forward switching drops the frame that does not pass the frame check sequence check. Therefore, it does not forward invalid frame, but in contrast, the cut-through switching method may forward invalid frames because there is no frequency frame check sequence check is performed. Therefore, cut-through switching has the ability to perform rapid frame switching. This means that the switch can make a forwarding decision as soon as it looked up the destination MAC address of the frame in its MAC address table, as it is shown here in this figure. The switch does not have to wait for the rest of the frame to enter the ingress port before making its forwarding decision. Fragment-free switching is a modified form of cut-through switching in which the switch only starts forwarding the frame. Fragment-free switching provides better error checking than cut-through, which particularly there is no increase in latency. The lower latency speed of cut-through switching makes it more appropriate for extremely demanding high-performance computing applications that require process latencies for 10 microseconds or less. The cut-through switching method can forward frames with errors. If there is a high error rate with invalid frames in the network, cut-through switching can have a negative impact on the bandwidth and thereby clogging up bandwidth with damaged and invalid frame. And here is an activity which is called SWITCH-IT. It's the activity to check the understanding of how a switch learn and forward frame. And here we have the frame that comes, which is given the destination MAC address and the source MAC address. And here it is listed the MAC address table and what it is known for the moment in this MAC address table. And there will be two questions. The question for the first will be where will the switch forward the frame, and you have to identify by the frame and the MAC address table, you have to identify the egress port here. And the second question will be when the switch forward the frame, which statement will be true. So you have to identify if the frame is unicast, broadcast, and if it will be flooded out of the ports if there isn't the egress port listed in the MAC table, or it will be sent to a specific port only if the egress port is listed in the MAC address table, or if the switch adds the source MAC address with its current information that is not in the MAC address table. So let's see some examples. Okay, now it's working. So for the moment we have the information, and for this information the switch will forward the frame on these ports, and these are the statements that are true. This is the second one, and so let's go. Every time you have to check the frame, the MAC address table, and by this information you have to provide the information for the question 1 and the question 2. So, in legacy hub-based Ethernet segments, network devices competed for the shared medium, which means that the network segments that share the same bandwidth between devices are known as collision domains. And when two or more devices with the same collision domain try to communicate at the same time, a collision will occur. If an Ethernet switch port is operating in half duplex, each segment is in its own collision domain. And there are no collisions when switch ports are operating in full duplex. However, there could be a collision domain if a switch port is operating in hard duplex. By default, Ethernet switch port will auto-negotiate for the full duplex, where the adjacent device can also operate in full duplex. If the switch port is connected to a device operating in hard duplex, switch such as a legacy hub, then the switch port will operate in half duplex. And in this case, the switch port will be part of a collision domain. Here it is a figure that shows the full duplex is chosen if both devices have the capability along with their highest common bandwidth. A collision of an interconnected switches forms a single broadcast domain. Only a network layer device such as a router can divide a layer 2 broadcast domain. Routers are used to segment broadcast domains, but will also segment a collision domain. When a device sends a layer 2 broadcast, the destination MAC address in the frame is set to all binary ones. The layer 2 broadcast domain is referred to as the MAC address broadcast domain. The MAC address broadcast domain consists of all devices on the LAN that received broadcast frame in from a host. And here it is an animation that shows the broadcast domain and collision domain. When a switch receives a broadcast frame, it forwards the frame out each of its ports. Expect the ingress port where the broadcast frame was received. Each device connected to the switch receives a copy of the broadcast frame and process it. Broadcasts are sometimes necessary for intentionally locating other devices and network services, but they also reduce network efficiency. Network bandwidth is used to propagate the broadcast traffic. Too many broadcasts and a heavy traffic load on network can result in congestion, which slows down network performance. When two switches are connected together, the broadcast domain is increased, as seen in the second half here. In this case, a broadcast frame is forwarded to all connected ports on the switch 1, and the switch 1, since it is connected with the switch 2, the frame is also propagated to all devices connected to the switch number 2. LAN switches have special characteristics that help them alleviate network congestion. By default, interconnected switch ports attempt to establish a link in full duplex, therefore eliminating collision domains. Each full duplex port of the switch provides the full bandwidth to the device or devices that are connected to the port. Full duplex connections have dramatically increased LAN network performance and are required for 1 gigabit per second Ethernet speeds and higher. Switches interconnect LAN segments by using a MAC address table to determine egress port and can lessen or eliminate collision entirely. Characteristics of switches that alleviate network congestion include the fast port speeds, which is an Ethernet switch port speed that vary by model and purpose. For instance, most access layer switches support 100 megabit per second and 1 gigabit per second port speeds. Distribution layer switches support 100 megabit per second, 1 gigabit per second, and 10 gigabit per second speeds, and core layer and data center switches may support 100 gigabit per second, 40 gigabit per second, and 10 gigabit per second speeds. Switches with faster port speeds cost more but can reduce the congestion. There are also the fast internal switching, where switches use a fast internal bus or shared memory to provide high performance. And we have even the large frame buffers, where switches use large memory buffers to temporarily store more received frames before having to start dropping them. This enables ingress traffic from a faster port to be forwarded to a slower egress port without losing the frames. And lastly is the high port density, where a high port density switch lowers overall cost because it reduces the number of switches required. For instance, if 96 egress ports were required, it would be less expensive to buy two 48 port switches instead of four 24 port switches. High port density switches are also help to keep the traffic local, which helps alleviate the congestion. And that is all about the switching concept. Thank you for being at the FinetLink channel. Do not forget to subscribe to this channel if you are new, and hit the notification button for the new videos that will be uploaded. And if you like this video, share it with your friends. See you to the next session.